Write the heading, bonding in coordination compounds. Bonding in coordination compounds. Again the subheading is VBT, valence bond theory. So why some are vacant? Sick or they went to this Christmas holidays. Really sick or so-called sick? Okay. So our heading is VBT, valence bond. Actually, if you look at the VBT of chemical bonding, VBT we have discussed at two places. One is at chemical bond, the other is at we write VBT like that. Divide it into two types. Chemical bonding. Okay, listen to the explanation first. So in chemical bond, the VBT, what it says, a chemical bond is formed by the dash. According to valence bond theory, in the chapter of chemical bonding, how a chemical bond is formed due to the overlap of half-filled atomic orbitals. That is the first point. So VBT dividing we have two types, chemical bonding, second one is coordination compounds. VBT term we come across at two places. One is in chemical bonding chapter, the other is in coordination compounds. So I am giving the salient features in both the chapters. So in chemical bonding, according to VBT, a chemical bond is formed due to the overlap of half-filled atomic orbitals. That is the first point. What is the second point? Greater the extent of orbital overlap, greater is the strength of the bond. That is the second point of VBT in chemical bond. Greater the extent of orbital overlap, greater is the strength of the bond. What is the third point? In the process of orbital overlap, the spin of the electrons is neutralized during the process of orbital overlap. The spin of the electrons is neutralized and energy is released. Bond is established. Types of orbital overlap. Next point. In VBT of chemical bond only. Types of orbital overlap. Can be end-to-end, can be end-to-end or axial overlap. End-to-end or axial overlap. Which results in sigma bond. What is the second type? Lateral or sideways overlap. Lateral or sideways overlap gives pi bond. What is the next point? Sigma PP overlap is greater than sigma SP overlap is greater than sigma SS overlap greater than pi PP. So actually this is the decreasing order of extent of orbital overlap. But 1s overlap is the strongest overlap. And hence HH single bond is the strongest single bond in the periodic table. Actually, these I should not discuss now because we already discussed in chemical bonding chapter. But student may think he had already experienced some VBT. Again, here we are putting VBT heading. So what is that difference? That VBT and this VBT. So to explain that, I have given the important points of the VBT of chemical bond. Now we are going for VBT in coordination compounds. Our heading is VBT in coordination compounds. First point, the metal atom or a metal ion in a complex the metal atom or metal ion in a complex provides vacant orbitals for bonding. Second point, the vacant orbitals mix with each other and form vacant hybrid orbitals. The third point, if n-1d, comma ns and np orbitals are involved in hybridization. It is called B2sp3 hybridization. Within bracket, inner orbital complex or low spin complex. And if ND, NS, and if NS, NP and ND. NS, NP and ND. Orbitals are involved. In hybridization. The hybrid orbital, the hybridization is known as sp3d2. Within bracket, outer orbital complex. Or high spin complex. So the V-between coordination compounds is very simple. The central metal atom or ion provides what? Vacant orbitals for bonding. And second point is, these vacant orbitals mix with each other and form vacant hybrid orbitals. Now in the formation of these vacant hybrid orbitals, if n-1 d orbitals are involved in hybridization, it is called D2sp3. If outer nd orbitals are involved, it is called sp3 d2. So based on this, if you look at some examples directly, you can see. So write the first example for VBT. Nickel tetracarbonate, NiCO 4 times. Nickel tetracarbonate, we will give the first example. Nickel 28 with 0 oxidation state. This is 3D8. 4:4 P0. Now in this, when 4 CO molecules approach nickel in 0 oxidation state, nickel atom provides vacant orbitals for bonding. So the first example we are going to discuss is the formation of nickel carbonate. So in the nickel carbonate, what is the central metal atom? Nickel. In what oxidation state it is? 0. How many carbon monoxide ligands are approaching nickel? 4. So nickel should provide 4 vacant orbitals. Nickel atom provides vacant orbitals for bonding. It should provide four vacant orbitals for 4 CO molecules and is possible only after electronic rearrangement. So what is this electronic rearrangement? I am going to write now. There are two s electrons must pair here. Then the configuration becomes 3d10, 4s0, 4p0. What is the electronic rearrangement? Two s electrons went into the d orbital and got paired there. So that is when that s electrons go into d and pair here, then nickel can provide 4 vacant orbitals, and these vacant orbitals mix with each other. Mixing is called hybridization. When S and 3p are mixed, the hybrid orbitals formed are 4 sp3 hybrid orbitals are formed. Four sp3 hybrid orbitals are formed around nickel in zero state. With these 4 sp3 hybrid orbitals, nickel can form 4 coordinate covalent. This is nickel carbonyl. So what is the hybridization of nickel here? sp3. Whenever sp3 hybridization occurs, what is the shape of the molecule? Tetrahedral. Here CO is acting as electron pair donor. Electron pair donors are called Lewis bases. So nickel, central atom nickel is electron pair acceptor. It is a Lewis acid. So here 4 carbon monoxide molecules are acting as Lewis bases or ligands. Lewis bases are also nothing but ligands. And the central metal nickel is Lewis acid. So this is the first example. Second example you write. Iron carbonide. Iron carbonide FeCO 5 times with 0 oxidation state. Nickel is having, iron is having 0 oxidation state. What is iron electronic configuration? The atomic number is 26. Three D6, 4s2, 4p0. How many CO are approaching iron? 5. The iron should provide 5 vacant orbitals for bonding. That's an electronic rearrangement. Electronic rearrangement. Occurs. After the electronic rearrangement, the two s electrons are going to pair here. So it becomes 3d8. So these two come and pair here. These two again pair here. So 3d6 become 3d8. 4s become 4s0. Already 4p0. So which orbitals are going to mix? 1d, 1s, 3p. So the hybridization is dsp3. How many dsp3? Total how many are mixed? So 5 dsp3 hybrid orbitals. 5 dsp3 hybrid orbitals. Using these 5 sp3 dsp3 hybrid orbitals, the iron forms 5 coordinate covalent bonds with 5 carbon monoxide molecules. So central atom iron dsp3, trigonal bipyramidal. Example 3, CONH3. Six times Cl. CONH3 6 times Cl. Here CO is in which oxidation state? CO is in +3 oxidation state. In +3 oxidation state, so cobalt is 3d7 4s2. Then the electrons will be 3d6 4s0 4pg. Actual cobalt configuration is 3d7 4s2. +3 means how many electrons you have to remove? Then becomes CO3 plus. So then the configuration become 3d6 4s0. Here I wrote how many ammonia molecules are approaching cobalt 3 plus ion. 6 ammonia molecules. They approach cobalt 3 plus ion. Then cobalt 3 plus ion must provide 6 vacant orbitals for bonding. So cobalt 3 plus after electronic rearrangement it becomes 3d6 4s0 4p0. Here look at this. These 3d6, 4 single electrons become 2 pairs. That is I have shown here. So after electronic rearrangement, cobalt 3 plus has a configuration of 3d6, 4s0. Now which orbitals are going to hybridize? n minus 2, n minus d, sp3. So the hybridization will be d2, sp3. 6 d2, sp3. Hybrid orbitals. Will be formed. Is the inner d orbitals are participating or outer d orbitals? Inner, outer shell is 4th shell. Inner shell is 3rd shell. That's why the complex will be inner orbital complex, which is also called low spin complex. So here the shape of the complex is octahedral. So 6 ammonia molecules donate 6 lone pairs into the vacant hybrid orbitals of cobalt 3 plus. 3 plus. To balance the 3 units of positive charge, 3 Cl minus ions will be there. So as a whole, the complex ion shape, octahedral. Hybridization is D2sp3. Inner orbital complex. Inner orbital complex or low spin complex. For tomorrow's homework, because I have given 3 examples. Now you have to write for practice. Number 1, CuNH3 4 times SO4. AgNH3 twice Cl. Third one, CrCO 6 times. Fourth one, NiCN 4 times 2 minus NiCl4 2 minus K4 FeCN6 potassium ferrocyanide. Potassium ferricyanide. NiH2O 6 times 2 plus MnCl4 2 minus FeF6 3 minus So all these we will write in a similar way. Just now how I wrote the electronic configuration, how the metal ion is providing vacant orbitals for bonding, how the vacant orbitals are mixing to form hybrid orbitals. PtCl4 2 minus So all these, today evening the study over 5, tomorrow 5, over. We will add some more to the list. So this is all about VBT. Very simple VBT. What the metal ion will do, it will provide vacant orbitals for bonding. The vacant orbitals, not pure orbitals, they mix with each other and form what? Hybrid orbitals. And these hybrid orbitals are going to receive electrons from the ligands. So metal ion is acting as a Lewis acid. The ligands are acting as Lewis base. Formation of a complex is neutralization according to Lewis acid base theory. NiCl4 we already completed. NiCl4 I give now in the list. CONS3 we have given already. Limitations of valence bond theory. Cannot explain the magnetic properties. First point you write. Cannot explain the magnetic properties and the color of the complex. Cannot distinguish why complexes with 4 coordination number will have 2 shapes, tetrahedral and square planar. Cannot explain why complexes with 4 coordination number can have 2 shapes, that is tetrahedral, and the second one square planar. The next one, last one, cannot differentiate the strength of the ligands. The strength of the ligands. Next, write heading crystal field theory, CFT. This theory explains the ionic nature of complexes. This theory explains the ionic nature of the complexes. Ionic nature of the complexes. Number 2. Point number 2. The bond present between the metal ion and the ligand is purely electrostatic. That is, ionic bond. Number 2, ligands are considered as point charges. Point charges. Point number 3, when the ligands within brackets point charges approach the metal ion, approach the metal ion, repulsions exist. Repulsions exist between the lobes of the d orbitals of the metal ion. Repulsions exist between the lobes of d orbitals of the metal ion and the ligands. Full stop. Next point. The repulsions between the ligands and d orbitals the d orbitals and the ligands will increase the energy of the d orbitals and also cause the splitting of d orbitals into two sets. The splitting of d orbitals into two sets. The dx square, y square and dz square orbitals. The dx square, y square and dz square orbitals directly face the approaching ligands. Directly face the approaching ligands. That causes higher energy Now the diagram you can easily follow in this. NT2G. NT2G and NEG represents where CFS is called crystal field stabilization energy. Crystal field stabilization energy. NEG and NT2G represents the number of electrons NEG and NT2G represent the number of electrons in the EG and T2G orbitals respectively. So just I will read out any important points in CFT. For you, no need of worrying about visibility and all. So this is the diagram just now I have given. Splitting of d orbitals into two sets. So when 6 ligands, 1, 2, 3, 4, 5, 6, L means ligand, central metal M, approaching, the 5 d orbitals are splitting into two. One is EG set, the other is T2G set. This is easy. The lower one is T2G. So here only some important points are there, we will do it. So write this formula. Delta naught CFSC, same formula I wrote, but in a different form also you can write. Delta naught CFSC is equal to minus 4 into n electrons of T2G minus 4 into n electrons of T2G plus 6 into n electrons of EG, that is in the form of TQ. So this one, earlier I wrote in form of delta naught, here what they have written in form of dq. Write the next point. Filling of EG orbital filling of EG orbital increases filling of EG orbital increases its energy by a factor of 3 by 5 delta naught per each electron and filling up T2G set lowers its energy content by 2/5 delta naught per each electron. Next point. The delta naught CFSE depends on the delta naught CFSE, crystal field stabilization energy or crystal field splitting energy. So the delta naught CFSE depends on number one, geometry of the complex. Number two, oxidation state of the metal ion. Number three, size of the metal atom or ion. Number four, strength of the ligand field. Strength of the ligand field. This point make a very important point. So what is this point? The delta naught CFSE depends on the geometry of the complex, oxidation state of the metal ion, size of the metal atom or ion, and the strength of the ligand field. Next point. Ligands which cause greater splitting between between EG and T2G are said to be strong field ligands and ligands which cause less splitting between T2G and EG are known as weak field ligands. Weak field ligands. We'll stop the next point. The spectrochemical series gives the increasing order increase the increasing order of the ligand field strength. The spectrochemical series gives the increasing order of ligand field strength which follows. Write the order: I minus less than, Br minus less than. Third one is SCN minus. Please see this order: I minus, Br minus, SCN minus, next is Cl minus, less than S2 minus, less than F minus, less than OH minus, less than C2O4, 2 minus, less than H2O, less than NCS minus, next EDTA 4 minus, less than EN, ethylene diamine, less than Cn minus, less than CO, you write these 4: ammonia, ethylene diamine, cyanide and CO, mentioned as strong field ligands. These 4 are strong field ligands. These 2, NCS and EDTA, moderately strong. From water to all these, water, oxalate, OHF, all these are weak field ligands. Weak field ligands. I minus is the weakest ligand. I minus is the weakest ligand, and carbon monoxide is the strongest ligand. What this entire series is called? Spectrochemical series. From left to right in periodic table, from left to right in the periodic table, in second period, in the second period, the strength of the ligand field decreases in the order carbon donor greater than, nitrogen donor greater than, oxygen donor greater than, halogen donor. C donor greater than nitrogen donor, greater than oxygen donor, then last one is halogen donor. Next point. For D1, D2, D3 coordination entities, for D1, D2, D3 coordination entities, the d electrons occupy the D2G orbital singly as per Hund's rule. Full stop, a comma, and for D4 ion, and for D4 ions, the fourth electron could enter the D2G level with pairing, could enter the D2G level with the pairing, or the easy level or the easy level. Look at this, whatever I have given. This is the energy axis. The 5d orbitals, when they split into two sets, T2G set, EG set, D1, the only single electron should occupy the lower energy T2G. So configuration become T2G1 EG0. So for D2, configuration, again, the second electron This is D2 configuration. This is D1 configuration. So what is D2 configuration? It is T2G2 EG0. Now I am writing D3 configuration. D3 also, the 3 electrons will occupy then the configuration becomes T2G3 EG0. So D1, D2, D3 configuration is saved in strong field ligands or weak field ligands. So whether it is D1 or D2 or D3, the lower energy T2G is occupied first. So it is T2G3 EG0. But if you look at D4, for D4 configuration, it depends on how the d orbitals split. If the d orbital split to maximum extent, strong ligand field in the strong ligand field only, the 4 electrons D4, after filling the 3 electrons in the T2G set, now the 4th electron will have 2 choices: pairing with the D electron or going to the EG. It can pair here or it can go to the other. So right, if delta naught is greater than pairing energy, the 4th electron pairs in the T2G set. And is only possible in strong ligand field. Then CFSC becomes crystal field splitting energy in tetrahedral field. With the sound because of these are outside. No, even it is open. Open also it is giving the same sound. So, confirm. Maybe the physics characters are used completely. Before me, physics are no. You might have completely utilized. Yesterday, actually, I wanted to meet him. I'm in Calcutta yesterday. Not placing in the pocket. Okay, see the difference between TH and OH. Actually, this is octahedral field. So the ligand, 6 ligands approach. 2 from this axis, 4 from the 4 corners. This is an octahedron. The octahedron is approached by how many L? 6. Whenever the coordination number is 6, L means ligand. 6 ligands means 6 coordination number. Then the shape of the molecule is octahedral. So when 6 ligands are approaching, 4 from the 4 corners of a square, 2 from the axial position, which lobes of d orbitals are directly facing the ligands? The 2 lobes of dz square. This is dz. This lobe is directly facing the ligand. Similarly, this lobe is also facing ligand. And this is dx square, y square. So how many lobes of dx square, y square? Total 4 lobes. 4 lobes of dx square, y square. 2 lobes of dz square are directly facing the ligands. Ligand is considered as point charge. Ligand is considered as point charge and point negative charge. D orbital is also negative charge. Orbital means nothing but the place where the property of finding the electron is maximum. So electron is negative, ligand is negative, negative repulsions. So out of the 5 d orbitals, which d orbitals face maximum repulsion when ligands are approaching in an octahedral manner? Very good. dz square and dx square, y square. That's why in octahedral field, what is happening? The 5 d orbitals, initially with the same energy, are splitting into 2 categories. dx square, y square, dz square. These are facing maximum repulsion. That's why their energy is high. Their energy is maximum. dz square and dxy, dyz, they are not directly facing the ligands. That's why their energy is low. This is called a D2G set. This is called EG set. The splitting difference is called delta naught. Crystal field splitting energy or crystal field stabilization energy. What is delta naught? Is equal to CFSE. What is the meaning of CFSE? Crystal field stabilization energy or crystal field splitting energy. When compared to the average energy, it is called average. This average energy is also called barycenter. Or barycenter. BARY. So when compared to the average energy, 2 d orbitals are having higher energy, 3 d orbitals are having lower energy. When compared to these 3, these 2 have higher energy, total of 5. That's why it is called plus 3 by 5. Total how many d orbitals? 5 d orbitals. When compared to 3, these 2 are having higher. That's why it is called plus 3 by 5, delta naught. When compared to these 2, these 3 have lower energy. That's why it is called minus 2 by 5, delta naught. So the dxy, dyz, dzx, they are having lower energy. How much? Minus 2 by 5 of delta naught. The two d orbitals, dx square y square and dz square, they are having higher energy. How much? Plus 3 by 5 delta naught. So this we have discussed already in the previous class. Now in tetrahedral field, this diagram is not valid because this is octahedral field. So in TH, I draw one more diagram here. This is energy axis. 5 d orbitals, initial equal energy. So the dxy, dyz, dzx, T2g will have more energy. Damn easy. This is dx square y square and dz square. This is easy. This splitting energy is called delta T, not delta naught. Delta naught represents splitting energy in octahedral field. Delta T represents splitting energy in tetrahedral field. So, this is the Barry center or average energy. This is plus 2 by 5 delta T. This is minus 3 by 5 delta T. So, you may ask me, why dxy, dyz, dzx, why these are having higher energy in tetrahedral field? This diagram is related to tetrahedral field. The earlier diagram is related to octahedral field. What is these 5? D orbitals of equal energy. D orbitals of equal energy. Whenever equal energy orbitals are present, what we call degenerate orbitals. Coming back to this Perry, that is why these three are having higher energy. So actually in tetrahedral field, let us write a cubical structure. Actually, this is tetrahedral action. This is tetrahedral shape. Here the lobes of dxy, dyz, this is dxy or dyz. They face the ligands, the 4 ligands. The 4 ligands, when they are approaching a tetrahedron, whose lobes are facing directly? dxy, dyz, dzx, their lobes are facing. That's why their energy is more. But in the examination, the most important thing is octahedral splitting is caused by how many ligands? 6 ligands. Tetrahedral splitting is caused by how many ligands? So when 6 ligands, let us say, cause 1 unit of splitting, four ligands cause how many units of splitting? 4 into 1 by 6. That's equal to 2/3. In terms of number, octahedral field splitting is caused by 6 ligands. Tetrahedral field splitting is caused by 4 ligands. When 6 ligands cause 1 unit of splitting, 4 ligands will cause how much splitting? 4 into 1 by 6. That is 2/3 in terms of number. In terms of direction, here look at this. Look at this. Here the ligands, from how many directions the ligands are approaching in octahedral field. How many directions the ligands are approaching? 6 directions. Whereas in tetrahedral field, only 4 directions. So when 6 directions cause 1 unit of splitting, 6 directions cause 1 unit. 4 directions cause how many units? Again, in terms of directions, it is 2/3. In terms of number, it is 2/3. In terms of directions, it is 2/3. Total, it is 4 by 9. Delta T is equal to 4 by 9 of delta naught. This is most important for the examination. Student must know that. Because one examination, they gave the value in octahedral field. They asked the value in tetrahedral field. Students should multiply with 4 by 9. What is the question they created? Delta naught value is given. What they ask? Delta T value is asked. Delta T is equal to always 4 by 9 of delta naught. How do we get 4 by 9? I explained. In terms of number, it is 2/3. In terms of directional approach, it is 2/3. 2/3 of 2/3 is 4 by 9 of delta naught. That is what crystal field splitting in tetrahedral field.
So how do we get 4 by 9?
In terms of number, in terms of directions, there are two things here. Comparatively, when compared to octahedral field, this is octahedral field. So octahedral means a square should be there, 4 corners, 4 ligands should be there, 5th and 6th. Total 6 ligands should approach from 6 directions. Okay? So 6 ligands, let us say, they are causing some splitting of the d orbitals. Let us say the 6 ligands cause 1 unit value, whatever it is, 1 unit of splitting in octahedral field. How many ligands? 6 ligands, causing how much splitting? But in tetrahedral field, how many ligands are causing the splitting? Only 4. So when 6 cause 1 unit splitting, 4 cause how many unit of splitting? 2 by 3. That is one value, keep aside. It is in terms of number. In terms of directions, here 6 directional approach. From 6 directions the ligands are approaching. So directionally 6 directions. 6 directions are causing 1 unit splitting. In tetrahedral field only 4 directions. Cause how much? Again 2/3. So 2/3 of delta naught in terms of number, 2/3 of delta naught in terms of direction. So total is 2/3 of 2/3, 4/9 of delta naught. That is the relation between delta t and delta naught. So delta t is equal to 4/9 of delta naught. This is very, very important.
So we multiply them or add them?
Multiply.
So why do you multiply?
Because it is in terms, it is not adding. 2/3 of 2/3. Half means multiplication. 2/3 of 2/3. 2/3 of direction, 2/3 of number. Good. You have to ask questions like that. Whenever questions are asked, that is very important thing for the teacher also. We should also equip with all sort of doubts. Come directly to the nascent mind of the student. That is a newly generated doubt. So teacher should be equipped. Okay, now coming back. You write this one also. Crystal field splitting of d orbitals in square planar complex. So you require not this much. You just take this part. But they split into EG and T2G. But T2G again split into DXY, DXZ and DYZ. EG split into DX square, Y square, DZ square. So up to this. You write this is energy axis. Write a point. In square planar complexes, the lobes of X and Y are directly facing the approaching ligands. The lobes of X and Y are directly facing the approaching ligands. Hence, highest energies for dx square y square or the energy of d orbitals follow the order dxz is equal to dyz less than dz square less than dxy this is the increasing order of energy. Highest energy is for dx square y square. The next highest energy is dxy. Wonders of the world. Where is your sleep? God, totally. Good. Now she is eligible to become a doctor. She can treat patients without sleeping. Faculty. dxz or dzx, both are same. dzx or xz is equal to dyz. Because in the square planar, xy are maximum facing the approaching ligands. Like you take xenon tetrafluoride, XeF4. You have studied this already. Though it is not a complex, you have studied the shape of xenon tetrafluoride. Wherever the fluor is, that direction only xy orbitals will be there. This is called dx square y square. So 4 ligands, when they are approaching the 4 corners of a square, maximum repulsions come from x and y lobes. That's why these two have the highest. Next comes to the lowest jet factor. This is what in square planar complexes. Write this question. Arrange the following complexes in the order of increasing crystal field splitting. Arrange the following complexes in the order of increasing crystal field splitting. FeH2O 6 times 2 plus FeH2O 6 times 3 plus FeCl6 4 minus. That is a 1, 2, 3. I already explained this. Many times, almost 3 times I explained, fourth time again I am explaining. CuSO4 5H2, copper sulfate pentahydrate is called what? BuTO. How many water molecules are directly linked to copper? In CuSO4 5H2O, 4 water molecules are directly linked to copper. Aqua copper 2 ion. If CuSO4 5H2O, if some ammonia is added, why it turns into deep blue? Because the weak water ligands are replaced by ammonia ligands. It becomes CuNH3 4 times 2 plus. In CuSO4 5H2O, copper is surrounded by 4 water molecules. But if ammonia is added to CuSO4, what will happen? The stronger ammonia ligand replaces weak water ligand. So it all depends on what ligands are linked to the metal atom. So based on that, the electron will absorb energy and jump from T2G level to EG level. So here, 13th question, please look at. If you are not able to look at a weak display, I will read out. The question is, explain why hexacyano complexes of metals in +2 state are usually yellow, but the corresponding hexa-aqua compounds are often blue or green. See the answer they have given. Crystal field stabilization energy or splitting energy is directly proportional to strength of the ligand. So color of the complex is complementary to the color which it absorbs. I explained already titanium 3 plus with the D1 configuration. Titanium 3 plus has only one unpaired d electron. When titanium is surrounded by, in +3 state, 6 water molecules and form an octahedral complex with a D1 configuration, 3D1. When 6 water molecules approach titanium, the d orbitals split into 2 categories. What is a weak ligand? So D1 is here. So titanium +3 configuration is T2G1 EG0. Correct? In the presence of 6 water molecules. Now this electron absorbs green wavelength of light from the VGR. In the VGR, it absorbs what wavelength of light? 500 nanometers wavelength of light, and jumps from T2G to EG, which we call DD transition. When this green is absorbed from the visible light, how many wavelengths are remaining? 6 wavelengths are remaining. When all 7 wavelengths are there, it is violet light, it is white light. When green light is absorbed, the remaining 6 wavelengths appear in the form of purple color. That's why all titanium salts in +3 state are purple colored. So whenever a particular complex is showing a particular color, it all depends on what wavelength of light it absorbs. What wavelength of light it absorbs depends on the splitting of d orbitals. Suppose if the d orbitals split at too much distance, it requires more energetic light, then it absorbs violet light. Violet light is the most energetic light in the visible spectrum. Red light is the least energetic. Because violet light has a lambda of 380 nanometers. Red light has a wavelength of 760 nanometers. Wavelength and frequency are inversely proportional. When wavelength is less, frequency is more. When frequency is more, energy is more. So for that, the 13th question, the answer is why the hexacyano complexes in +2 state are yellow, while the aqua complexes are blue or green. It all depends on the cyanide is a strong ligand. Cyanide is the second most strongest ligand. First is carbon monoxide. See the spectrochemical series. CO is the highest. Next is Cn minus. So the two strongest ligands in our syllabus is carbon monoxide less than, which is greater than Cn minus. After that, third position is occupied by ethylene diamine, EM. Fourth position is occupied by ammonia. Fifth is occupied by EDTA. Fifth is occupied by EDTA. Sixth is thiocyanate ion, LCS. So the top 5 you remember. Similarly, the weakest 5 also you remember. Mostly halide ions are weak field ligands. Water is also a weak ligand. So all these account for our thing. What is the coordination number of Mn in Mn2CO 10 times? This we have to see. See, this is Mn2CO 10 times. So each manganese is surrounded by how many carbon monoxide molecules? 1, 2, 3, 4, 5. And there is Mn bond. So coordination number should be 6. Look at the answer what they have given. Mn forms octahedral complex. So write example, write the heading, bridged binuclear complexes. Bridged binuclear complexes. In bridged binuclear complex, you write example, one example, Mn2CO 10 times. Mn2 carbon monoxide 10 times. There is a bridge between Mn and Mn. And each Mn is surrounded by 5 carbon monoxide. Here also. Mn2CO 10 times. There is one more bridged binuclear complex. Two metal atoms bridged binuclear. I think this is CO, CO2. No, not CO.
CO2.
No, that is wrong. What I wrote. I will write one more.
Two copper again carbon.
Now I write Fe2CO9 times. Fe2CO9 times. This is also in our syllabus. Fe. There is one bridged CO. How many are over? 4, 6, 7, 8, 9. Fe2CO9 times. There is one more bridged binuclear complex. Now in the morning class, afternoon class, I have given this as a tetrahedral molecule, nickel carbonyl with sp3. This we already discussed. This also we discussed, trigonal bipyramidal. CrCO6 times. This is octahedral. sp3d2, not sp3d2, d2sp3. All metal carbonyls, take one more point. All metal carbonyls where metal carbon bond is present, are called organometallics. So organometallics, we already discussed, I think. Sigma bonded organometallics, pi bonded organometallics. Is it over or not? Yes or no? Okay, right here. Sigma bonded organometallics, example, Grignard reagents, CH3MgBr, sigma bonded organometallics. CH3MgBr, methyl lithium, so this point, this you can see, methyl magnesium bromide. Below you write Grignard reagent. All Grignard reagents are what kind of organometallics? Sigma bonded organometallics. Next is methyl lithium. CH3Li. The last one, C2H5, 4 times Pb. What it is? Tetraethyl lead, TEL. When I discuss TEL, very good. Anti-knocking agent in petroleum, in the automobile industry, petrol or diesel vehicles, to reduce their sounds, we use an anti-knock additive, that is tetraethyl lead, TEL. Why TEL was banned nowadays? Lead vapors are poisonous for the human beings. That's why in petrol filling stations, you see a caption, unleaded petrol. Next time when you happen to be in petrol station, filling station, you see the caption there. They mention unleaded petrol. Earlier it was leaded petrol because the lead compound is added to reduce the sounds in the engine. Sounds produced in the engine is called knocking property. To reduce the knocking property, we use an anti-knocking agent. Next, pi bonded organometallics. Pi bonded organometallics, give example. Jesus salt, Jesus salt, ZEISIES, not Lord Jesus. This is Jesus salt. Its structure also you have to write. K plus square bracket begins. K plus square bracket begins. PtCl3 and one ethylene molecule is there, C2H4. Total square bracket minus.
Again, sir. Again. Repeat.
Repeat. K plus square bracket begins. Platinum is linked with 3 chlorines by direct dative bonds. One ethylene molecule donates its pi electrons. This is sigma bond, this is pi bond. So the organic part, this is the organic part. Organic part, metal is linked by what bond? Pi bond. That's why it is called a pi bonded organometallic. The second one is ferrocene.
So how do you distinguish between sigma and pi bond?
Bond energy. Sigma bond energy is different from pi bond energy. Pi bonds are weak bonds always. Moreover, the pi bonded electron cloud is donated to satisfy the 4 coordination number. Platinum usually forms 4 coordination complexes. 3 coordination number, 3 bonds are normal dative bonds formed by chlorine. The 4th bond, dative bond, is formed by the donation of the pi electron cloud of the ethylene molecule. Ethylene molecule C double bond C. Double bond always 1 sigma, 1 pi. Sigma is rigid, it cannot be donated. So pi electron cloud only can be donated. Thus it is a pi bonded organometallic. Second example, ferrocene. Ferrocene is a sandwich compound in which cyclopentadienyl anion What it is? Cyclopenta dienyl. Two enes are there. And one more cyclopenta dienyl anion. How many cyclopenta dienyl anions? 2. This negative part, pi bond are in conjugation. Here also the negative charge, pi bond are in conjugation. That's why if you take that cyclopenta dienyl anion, there is completely delocalized negative charge or electron cloud. So that pi electron cloud from one ring above, one ring below, there is iron 2 plus in between. Iron 2 plus 2 units of positive with vacant orbitals is searching for somebody to give some negative charge or donate electron pair to form bonds to stabilize it. Here 2 rings say, my dear iron 2 plus, don't worry, you have a delocalized electron cloud. We will donate that electron cloud to you and you can be sandwiched between us. That's why ferrocene is called a sandwich compound. Which are the following is a sandwich compound? The answer is ferrocene. Or in matching type, sandwich compound they give one side, other side ferrocene they will give. So the next one is dibenzene chromium. Here between 2 benzene rings, a chromium atom is sandwiched. So these 3 are examples of what? Pi bonded organometallic. The third one, sigma and pi bonded organometallics. Sigma and pi bonded organometallics.
So, what does that symbol eta represents there? Symbol eta, sorry, in the...
Eta represents the number of carbons involved in the ring. Eta power 5 means 5 carbon ring. Here eta power 6 means 6 carbon ring. That's not required for it, that's why I did not disclose that. Between Fe2 plus 2 cyclopentadienyl ring, each cyclopenta ring has 5 carbons. So that eta power 5 represents 5 carbon ring. Similarly for dibenzene chromium, it is eta power 6. Good. Students, now I am feeling very happy that they are interacting and asking questions. So if this is there from the beginning, you might, now your position will be somewhere. Almost nearer to medical college. Still you have time, don't worry. That the past is past, dead is dead, future is infinite. So you have infinite future. I will also write NEET after 9 more years. When you enter into your super specialty, I will join in a medical college. I have one option that. I have 2 options in my career now. One is to do some advanced research. That is, I always prefer that. Second is to time pass, study medicine. No human physiology, biochemistry. For interest, not for earning money or doing something. So these are the 2 options for me. Okay. Sigma and pi bonded organometallics. So this I think I discussed already. Can somebody explain that? All metal carbonyls are examples of sigma and pi bonded organometallics. Synergy, why the bond length increase, decrease, etc., etc. Everything in detail I discussed. So, can anyone recall at least the face feeling that yes, we have some? No. No facial feeling also. Okay. Okay, very simple. I'll explain, don't worry. Actually, in metal carbonyls, why they are called sigma and pi bonded? What's this here? Okay, here I get some space. So morning, afternoon class also we discussed nickel carbonyl. Nickel and carbon monoxide react. This is actually CO structure. CO structure. So carbon donates electron pair to nickel. If you look at the afternoon notes, you see how the electronic rearrangement of nickel. 3d8 4s to become 3d10 4s0 4p0. Correct? So after donating electron pair by carbon of the carbon monoxide, the full-filled d orbital of the nickel metal, we have 3d10 configuration. 5 d orbitals are fully filled in nickel in zero state. So the full-filled d orbital of the nickel want to back donate one electron pair to the vacant orbital, anti-bonding orbital of the carbon, which is called pi star, which is called anti-bonding molecular orbital. What nickel says, my dear carbon monoxide, when you approached me, I provided vacant orbitals for you as per VBT. As per VBT, the metal atom or ion will always provide vacant orbitals for bonding. The vacant orbitals mix with each other and form vacant hybrid orbitals. So nickel carbonyl, nickel is sp3 hybridized. So these vacant hybrid orbitals receive electron pair from the ligand, and a coordinate covalent bond or a day2 bond is formed. Up to that, fine. Now one more thing is happening, extra thing here. So that is, after accepting the lone pair, so metal put forward another proposal. Anyhow, I have completely filled d orbitals with me. You have vacant anti-bonding molecular orbital with you. In return, I will donate an electron pair to you. So here two bonds are formed. In one direction, sigma bond. In the reverse direction, lateral overlap. Who and who are lateral? One sigma and one pi bond. So this is the scenario. When a single bond, you are down. When a single bond become a double bond now, the bond energy increases. That is called a synergic effect. In matching type questions, synergic effect one column, metal carbonyl another column. You have to match it. What is called a synergic effect? The increase in bond strength due to a back bonding or due to the formation of an extra pi bond. So bond energy increases, bond length decreases. Between carbon and oxygen, initially it is a triple bond, now it became a double bond. So here bond energy decreases, bond length increases. Metal carbon, here two different questions. You should be very careful whether they are asking the metal carbon bonds or carbon oxygen bond. If the question is related to metal carbon bond, the bond strength increases because single bond becomes double bond. Bond length decreases. If they ask about carbon oxygen bond in metal carbonyls, the carbon oxygen bond length increases because triple bond becomes double bond. Carbon oxygen bond strength decreases. 4 questions. Already IIT NEET, many times these questions are, plenty of time these questions are asked, still they are going to ask. Now, you write one more point. There are some ionic organometallics. Ionic organometallics. Like N-butyl lithium, C4H9 minus Li plus. N-butyl lithium. What kind of organometallic it is? An ionic organometallic. Very dangerous. If I keep one bottle of N-butyl lithium, just unscrew the bottle out, this entire building catches fire. No need of giving any, just a matchstick is thrown or no, nothing. Just open the bottle, unscrew it, finish. Why that much? Who is the father of C4H9 minus? C4H10, butane. Father of C4H9 minus is C4H10. Butane is the weakest acid. Whereas carbon hydrogen bonds are less polar, least polar. When butane is least acidic, its conjugate base, butyl ion, is strongest conjugate base. C4H10, weakest acid. From acid, if you remove a proton, you get conjugate base. So what is the conjugate base of butane? Butyl anion. What is the formula? C4H9 minus. This butyl anion is so strong conjugate base, when it is exposed to air, it takes proton from the moisture of the air and becomes C4H10. It has strong proton abstracting tendency. From whom it takes the proton? From the moisture content of the atmosphere, air. It takes the H plus and converts into C4H10. So when a negative ion takes a positive ion and becomes a neutral molecule, energy is released. That energy catches the fire for the butane. Butane is a combustible gas. All hydrocarbons are combustible gases. All hydrocarbons, benzene, methane, ethane, butane, your domestic gas cylinder, butane and isobutane. Your mess, the gas cylinder they are using, it contains what gases? Butane and isobutane. So that's why n-butyl lithium is highly dangerous. Pyrophoric. In research lab, what we do? Nitrogen cylinders are there. There are balloons also, not inflated balloons, normal balloons. We take a balloon to the nitrogen cylinder and keep to the nozzle and open it. The balloon is inflated with nitrogen gas. That nitrogen gas balloon is covered to the n-butyl lithium body. Because now n-butyl lithium, if you unscrew it, now since I placed a balloon there, it is in nitrogen atmosphere. Nitrogen is highly inert in nature due to triple bond. Now I can safely draw n-butyl lithium from it. Directly I can't take n-butyl lithium. They are called pyrophoric compounds. Pyre means in Greek language fire. So pyrophoric means they easily catch fire. They are pyrophoric. Okay, now after this metal carbonyls, synergic effect is already discussed. Stability of coordination compounds. This is the last point in this chapter. Stability of coordination compounds is expressed in terms of stability constant. Stability constant. Larger the value of stability constant, greater is the stability for the complex. Greater is the stability of the complex. For example, I am giving Cu2 plus ammonia liquid CuNH3 plus 2 plus. Let us say the equilibrium constant K1 is equal to CuNH3 2 plus by Cu2 plus Cu2 plus into ammonia concentration. Now the CuNH3 2 plus added with one more ammonia ligand, what I will get now? CuNH3 twice 2 plus. Similarly, you can write K2 for this. CuNH3 twice 2 plus by CuNH3 single plus ammonia. Now the third equilibrium, CuNH3 twice 2 plus is added with one more ammonia. What I will get? CuNH3 thrice 2 plus. Similarly, you can write K3 for this. And the last one, CuNH3 thrice 2 plus is treated with one more ammonia. So I got CuNH3 4 times. 2 plus and K4 also you can calculate. If I want the overall reaction, this one cancels. This cancels. This cancels. So finally what I will get? Cu2 plus 4NH3 liquid gives CuNH3 4 times 2 plus. These are called stepwise stability constants. K2, K3, K4 are called stepwise stability constants. The overall stability constant is called beta. So beta 4 is equal to K1 into K2 into K3 into K4. Larger the value of beta, more is the stability for the complex. Larger the value of beta, greater is the stability for the constant, for the complex. Right, one more point. The reciprocal of the stability constant is called instability constant or dissociation constant. The reciprocal of stability constant is known as instability constant or dissociation constant. A small problem, please write that. Calculate the instability constant. Calculate the instability constant for NiNH3 6 times 2 plus. Given that beta 6 for this complex is 2 into 10 power 12. Given beta 6 is equal to 2 into 10 power 12. So K instability is equal to 1 by beta 6 reciprocal. So 1 by 2 into 10 power 12. They wrote it as 1 by 2 into 10 power minus 2. 1 by 2 is 0.5 into 10 power minus 12. Or 5 into 10 power minus 13. That is called instability constant. Now, see, write that note also, write all the 4 points. Stability of a complex is inversely proportional to size of the central metal ion, directly proportional to basicity of the ligand, directly proportional to charge on the metal ion, directly proportional to number of chelate rings. Note. Shall I write or is it visible?
Right.
Shall I write? Stability of a complex. We write in a different way. Is inversely proportional to size of the central metal ion / atom and directly proportional to basicity of the ligand. Directly proportional to charge on the metal ion. Directly proportional to number of chelate rings. We are discussing chelate rings. I already discussed in NiDMG twice. Nickel dimethyl dioxide. Yes or no? A dark red complex. So what are chelated rings? What are chelate complexes? So bidentate or polydentate ligands, when they are directly attached to the metal ion, they form ring compounds. They are called chelate complexes. Bidentate or polydentate. Bidentate or polydentate ligands when they are attached to the metal ion form ring compounds which are called chelated complexes or simply chelates. Example, NiDMG twice, nickel dimethyl dioxide. A dark red complex. Which of the following is more stable? Question number 14. K for FeCl6 or K3 FeCl6? Very good. So the answer is this. Due to higher oxidation state of iron. Next. Next one. CONH3 6 times 3 plus or COEN twice NH3 twice.
COEN twice.
Because here two EN rings, they form this is EN, this is EN. This is NH3. This is NH3. So it forms a ring. Ethylene diamine ring. So it is a semi-chelate, not a big ring. A 4-carbon ring is. So 1, 2, 3, 4. 4 carbons are involved in there. Not 4, 5. Pentagon is formed. So the answer is this. Next one. So stronger the ligand, more the stability. So CO, NiCl 4 times 2 minus is more stable than NiCl4 because Cl is a weak ligand, Cl minus is a strong ligand. Actually, effective atomic number, write 1 point, very simple only. Effective atomic number. A concept used to explain. It's a concept used to explain the stability of the complexes. The stability of the complexes. En is equal to the number of electrons present in the metal atom or ion. The number of electrons present in the metal atom or ion in a complex plus the total number of electrons contributed with the ligands. Plus the total number of electrons contributed by the ligands. If it equals to, if the sum is equal to the nearest noble gas configuration, if the sum is equal to the nearest noble gas configuration, we say the complex obeys EAN rule. The complex obeys the EAN rule. Example 1. NiCO 4 times. What are the total number of electrons of nickel? 28. Plus 4 ligands contribute 4 into 2 electrons. So total electrons become 36 electrons, which is equal to krypton configuration. So nickel carbonyl is obeying EAN rule. Or I take FeCO 5 times. So how much iron is having electrons? 26 electrons iron. Atomic number is 26. 5 carbon monoxides, each will donate 2 electrons. 5 into 2 electrons, 10 electrons. Each carbon monoxide donates 1 electron pair. Means 2 electrons. So again 36 electrons, which is equal to krypton. It also obeys EAN rule. Here one is given. K4FeCN6. So 26 iron. Not 26 because iron is in +2 state here. So iron +2 has only 24 electrons. Plus, how many ligands? Ligand always contribute 2 electrons if it is a monodentate ligand. So 6 cyanides contribute 6 into 2. Again 36. Again krypton configuration. Next, COEN twice, NH3 twice, 3 plus. COEN twice, NH3 twice, 3 plus. So cobalt 27 in +3 state, -3 electron, 24 electrons, plus 2 ethylene diamines. Each ethylene diamine contribute 2 dative bonds. It is a bidentate ligand. Means it donates 2 pairs. Means 4 electrons. So 2 ethylene diamines, 2 into 4 electrons. Plus 2 ammonias contribute 2 into 2 electrons. Is following? 8 plus 32, 32 plus 4, 36. It is also obeying effective atomic number rule. But look at K3FeCN6. Will it obey or not obey? Because iron is in +3 state here. 23 electrons. Plus 6 into 2. 35 electrons. Does not obey EAN. Play a vital role in performing the crucial functions. So once upon a time, when people are having bloodlessness, that means the bone marrow does not produce enough erythrocytes or RBC. RBC or erythrocytes are produced in the bone marrow. If enough RBC are not produced, the person will be having a disease called pernicious anemia. The person becomes pale, white in color. Not that all white persons are anemic. Some people become anemic and become white. Generally, female are more anemic than male because of hormonal problems. That is a universal truth. Female is having hormonal fluctuations. That's why they are always more anemic. That is number point number one. If a person is anemic, the person easily gets tired. He can't concentrate on his work also. And when the doctor observes the eye or the tongue, the pale color of the eye, the white tinge of the tongue, these are all doctors can easily recognize your anemic condition. They will ask you to go for a blood test. They ask to go for a blood test, it will give us the vitamin B12 quantity in your blood. If the vitamin B12 is deficient, you become anemic. So once upon a time, to treat this anemia, scientists worked a lot for almost 2-3 decades. They worked how to treat. Patients are piling up, anemic patients. They don't know how to treat, which medicine they have to give. For one batch of patients, what they have given, raw liver pieces in the food. Chicken liver, mutton liver. Raw liver is given to them. You swallow some pieces. When they swallowed, immediately their RBC has increased. They become very active. Then they thought this raw liver contained a particular substance that we have to isolate. So they found that the methylcobalamin is present in the raw liver. But to extract it, the methyl group is replaced by cyano group. So the cyanocobalamin form, it is recovered from the liver. That is vitamin B12. This is the earliest science development. But nowadays in the lab we make it. We don't take a liver and extract vitamin B12 from that. Directly we synthesize in the lab. This vitamin B12 tablets or capsules or injections are so versatile. Even doctor prescriptions also not required. Over the counter medicine. You can directly go and purchase it and use it. So anemia can be easily treated nowadays. But once it is a biggest issue. So that RBC factor, these are all caused by complexes. So this anti-pernicious anemia factor, it is very important. Wilkinson catalyst. In the hydrogenation of alkenes, its IUPAC name is chlorodris triphenyl phosphine rhodium. Rhodium 1. Chlorodris. The complex is pH 3 P total thrice RHCl. This is the complex. So what are the ligands that are linked to rhodium? One chlorine ligand, one triphenyl phosphine. What is triphenyl phosphine? pH 3 is phosphine. This is phosphine. In phosphine, 3 hydrogens are replaced by 3 phenyl groups. Then it is called triphenyl phosphine. pH means phenyl. So triphenyl phosphine, it contains a word tri. How many triphenyl phosphines are there? That's why if you want to name it triphenyl phosphine, you have to use word tri 2 times. Tri for this. Again triphenyl phosphine contains tri. So 2 times you have to use the word tri. That's why in such cases the UPAC has given tris. So chlorotris. Tris means 3 times. Triphenyl phosphide, rhodium 1 complex. This is called Wilkinson catalyst, used in the hydrogenation of alkenes. Not alkanes, alkenes. Next, in the development of photography, this I think I already discussed, okay. Anyhow, we discussed photography. Hypo is used as a fixing agent in photography due to the formation of a soluble complex. Argento Na3AgS2 twice. So dithiosulfato, sodium dithiosulfato, argentate 1 complex. So write that point. In the development of photography, a water-soluble complex is formed. A water-soluble complex is formed. When the silver bromide present on the photographic films forms a complex with hypo. Write that complex. Na3 AgS2O3 twice. Next, cancer tumors are killed by cisplatin. Cancer tumors are destroyed by cisplatin. What is cisplatin? The cis isomer PT NH3 twice Cl. This is called cisplatin. Next, EDTA is used EDTA is used. In the treatment of lead poisoning and also for determining the hardness of water. EDTA is used in lead poisoning, for treatment of lead poisoning, and also for determining the hardness of water. Okay, good. So actually, this visit I came with a specific purpose in my mind. The inorganic totally we completed, both of 11th and 12th. Some chapters of physical like atomic structure, thermodynamics. Thermodynamics may be only small part, spontaneity part is pending. Remaining part is over. And some problems. So, but we have not yet touched the organic part. So in this, by up to Sunday I am leaving again. So I am staying up to Saturday. By Saturday we will cover maximum organic of 11th and 12th.